Alright, so in this video I'm gonna be explaining this important article dropedge towards deep graph convolutional networks and node classification. This important paper in ICLR 2020, dropedge. So overfitting and oversmoothing are two main obstacles of developing deep graph convolutional networks for node classification. In particular, overfitting weakens the generalization ability in a small dataset, while oversmoothing impedes model training by isolating output representations from the input features with the increase in network depth. This paper proposes dropedge, a novel and flexible technique to alleviate both issues. At its core, dropedge randomly removes a certain number of edges from the input graph at its training epoch, acting like a data augmenter and also a message passing reducer. Furthermore, we theoretically demonstrate that dropedge either reduces the convergence speed of oversmoothing or relieves the information loss caused by it. More importantly, our dropedge is a general skill that can be equipped with many other backbone models such as graph convolutional network, ResGCN, GraphSage, JKNet for enhanced performance. Extensive experiments and several benchmarks verify that dropedge consistently improves the performance on a variety of both shallow and deep graph convolutional networks. The effect of dropedge on preventing oversmoothing is empirically visualized and validated as well. So the methodology is like this. At its training epoch, the dropedge technique drops out a certain rate of edges of the input graph by random. Formally, it randomly enforces VP non-zero elements of adjacency matrix to be zeros, where V is the total number of edges and P is the dropping rate. If we denote the resulting adjacency matrix, then its relation it becomes like this. So A prime is a sparse matrix expanded by a random subset of size VP from original edges. So we also perform the renormalization trick on a drop leading to a hat drop. We replace a hat and with a hat drop for propagation and training. Dropedge produces varying perturbations of the graph connections. As a result, it generates different random deformations of the input data and can be regarded as a data augmentation skill for graphs. To explain why this is valid, we provide an intuitive understanding here. The key in GCNs is to aggregate neighbors' information for each node, which can be understood as a weighted sum of the neighbor features. From the perspective of neighbor aggregation, dropedge enables a random subset aggregation instead of the full aggregation during GNN training. Statistically, dropedge only changes the expectation of neighbor aggregation up to a multiplier. If we drop edges with probability P, this multiplier will be actually removed after weight normalization, which is often the case in practice. Therefore, dropedge does not change expectation of neighbor aggregation and is an unbiased data augmentation technique for GNN training. similar to typical image augmentation skills, rotation, cropping, flapping, that are capable of hindering overfitting and training CNNs. We will provide experimental validation. Okay, so we can do it in a layer wise. So it's one shot with all layers sharing the same perturbed adjacency matrix. We can perform drop edge for each individual layer. Specifically, we obtain a hat drop by independently computing equation 2 for each elf layer. Different layer could have different adjacency matrix. Such layer-wise version brings in more randomness and deformations of the original data. Oversmoothing is another obstacle of training deep GCNs, and we will detail how drop edge can address it to some extent in the next section. So definition of epsilon smoothing is like this. We call the epsilon smoothing of node features happen for a GCN if all its hidden vectors beyond a certain layer have a distance no larger than epsilon. With respect to a subspace M that is independent to input features. Given the subspace M, we call the minimal value of the layers that satisfy this equation as the epsilon smoothing layer. My worry is that these methods don't always create a connected graph, because when you remove an edge, it may be a bottleneck, and it could lead to two separate graphs. So I want to see how this article deals with such situation. I want to investigate if there is such paragraph that indicates such phenomenon. We denote the original graph as G and the one after dropping certain edges as G prime. Given a small value of epsilon, we assume G and G prime will encounter the epsilon smoothing issue with regard to subspaces M and M prime respectively. Then either of the following inequalities holds after sufficient edges removed. The relaxed smoothing layer only increases. The information loss is decreased. So testing accuracy on different backbones, for example, PubMed if you use GraphSage on the PubMed dataset, you will see that we have this testing accuracy 90%. So if we increase the layers, then for example from 2 layers, if we go to 8 layers, then we have one more increase, 1% more increase, and then but if we go to 32 layers, then suddenly we have 47%. So the accuracy goes down. First it goes up and then it goes down as the number of layers increases. The accuracy changes. So this is a good observation.